We can start now. Riley, time?
Yes, sir.
Yes, sir.
For some reason, I'm not seeing the slides now. Are they still there?
Sir, I had stopped sharing.
Okay, so it's again a pleasure to welcome and introduce my colleague and a very distinguished computer scientist, Sunita Saravagi. She is a professor in computer science and engineering department in IIT Bombay and also heads the Center for Machine Intelligence and Data Science in IIT. I'll just briefly go through her highly kind of impressive CV. She did her BTech in IIT Kharagpur and Masters and PhD in UC Berkeley. She worked for a few years in IBM Almaden before joining Computer Science and Engineering Department at IIT Bombay, where she has been ever since. This also includes visiting positions at Carnegie Mellon University and Google. She has won several awards and honors. To mention a few of them, she is a distinguished alumnus of IIT Kharagpur. She has won the Infosys Award. She has won the Most Influential Paper Award from PAKK conference in 2014 and the Best Paper Award of ACM Sigmod in 1998. She has worked in very broad areas of machine learning. And today she will talk about robustness to change in machine learning model. And before I hand over to her, let me just inform the audience that they can type their questions into the Q&A box and I'll read them out to Sunita at the end of her talk and she'll respond to them. So over to you, Sunita.
Thank you, Professor Borkar. Thanks a lot to the organizers for inviting me. It's an honor. And I hope you will get something out of the talk. So I will like to share my screen. Could I, if...
Yeah, ma'am, please.
Yes. Okay. So I hope my slides are visible now. So today I'm going to reflect on how well modern machine learning models handle changes during training and test distributions. Machine learning is now used in a diverse set of applications across many different data modalities. However, the core principle driving the training of machine learning models is disarmingly simple. So we assume that there is a latent distribution. So we are considering classification problems where the input is X and the label is Y. And before we start creating a model, we have this mental map that there is a latent joint distribution between X and Y. And the training data D is nothing but a sample from this joint distribution. So we might be given, say, n samples, x1, y1 to xn, yn. And during training, during machine learning, all we do is to fit a model of the probability of the class label, which is what the machine learning model needs to predict, given the input X. And this estimate needs to sort of resemble the latent distribution based on the samples that are given. Now, a standard method for training, for estimating this conditional distribution is based on the maximum likelihood estimation principle. So in order to apply that, we take two steps. First, we represent the probability y given x distribution as a parametric function, which is basically something, it's a function which takes as input an x and has parameters theta. And typically this is like a continuous function and often it's a differentiable function too. So this is a function and we find the theta so as to maximize the conditional likelihood of the data D. So you do this argmax over all possible theta for which over all your training example, the log of the probability of the given label in the samples, based on the function is maximized. And there are often some mild constraints to prevent you from overfitting on your training data. And this basic principle basically is behind behind all kinds of models, be it regression models or classification models or even structured learning problems. If you talk about image classification or automatic speech recognition, almost all of them basically use this maximum likelihood principle for training. They might call it cross entropy or some other margin-based classifier, but the statistical premise is the same. Now, why is this a good idea? So the reason this idea has stood for so long is because we believe that if we maximize the likelihood of predicting the Y for the samples which are drawn from the latent distribution, then if we see more samples from the same distribution, then we will generalize. Now, this is a very reasonable assumption to assume that during testing, that when you actually put the model to use, you will be seeing more samples from the latent distribution from which the training samples were obtained. This is a reasonable assumption in the classical controlled setting. Say when you train a classifier within a lab or within an enterprise, like say State Bank of India trains a model, okay, on their data. So this has been like the classical setting. It has kind of served well for almost 50 years, but this is not okay in the modern machine learning regime, where because of the huge success of machine learning and also because of the huge cost entailed in training machine learning models, typically large resource-rich organizations train the model and their data is hidden from the users of the model. They just release the model to be used by all and sundry. So in such cases, the distribution on which the model is deployed is often not the same as the training distribution. So more and more, we are sort of in this regime where the model needs to handle change. Now, of course, if the deployment distribution is so different and just totally if it has nothing to do with the training distribution, then we cannot do anything. And the best we can do is to just detect that we are getting a sample which is outside the training distribution and back off from making any prediction. By the way, even this is a very hard problem, and doing it in the context of deep learning is now also a topic of active research. But in this talk, we are going to assume that we only have to handle gradual and natural change, of the kind which humans would not even notice. And we will show that even for very natural, like non-adversarial changes, many state-of-the-art machine learning models suffer. So we are going to demonstrate this with some examples of our testing state-of-the-art machine learning models that we did in our lab. So first, we considered an automatic speech recognition model, which is available on the cloud. So this has been trained, using data which was collected by Google, and they, by just some very crude guess, maybe they have trained the speech recognition model on 50,000 hours of training data. And there is this data set, Mozilla Common Voice data set, which fortunately has this very rich data where the same sentence is spoken by users with very different accent. So if you take the data and you look at the sentences which are spoken by users, say from US, who are, who have, let's say, the predominant American accent, you get a word at a rate of 13%. Whereas for the same set of sentences, now if you switch to an Indian accent, you get only 22, you get as high as 22% WER. And even for an Australian accent, the error is large and you get 23% sort of WER. So here you see the lack of robustness of an ASR model to accent change. Here is another example of a more robust scale. Say, suppose, we had this problem where we were trying to train a handwriting recognition system. And this is trying to identify characters in Tamil. And we have, like, say, training data where we have collected samples of, 50 people. And now you train a model. And if you test it on more samples from the same set of 50 users, you get 90% accuracy. Whereas if you include 20 new people, then the accuracy drops to 83%. So, just the lack of generalizability to person change. I mean, that seems a bit alarming because, the whole point of training a handwriting recognition model is to, generalize across the handwritings of many different people. Here is another example. So this one we will consider a regression problem. So here this data was trying to predict, forecast the sales of a particular Walmart store in California. And there was training data collected over several years. And suppose if you use the training data from February 2013 to December 2015, and so this gave us 36 months of training data. And if you evaluate the trained regression model on data which is drawn from the same period, you get only 1% error. Whereas if you test it on January 2016 data, you get as high as 17% error. So here, these are 3 examples of lack of robustness, and there are several others. Off and on, you see these news articles which try to kind of make a big deal of the lack of robustness of deep learning. But, again, I want to stress that we are not interested in, sort of ridiculing ML models for lack of robustness in the adversarial setting. But what we just want to sort of focus on is sort of a very non-adversarial natural changes and see how we can make machine learning models adapt to natural changes. So, the key insight based on this goal that we exploit is that, classically, when we applied the maximum likelihood estimation principle for training the ML model, we assumed that the training samples are IID sample from that PXY distribution. And just going by the no free lunch theorem, what we say is that if you want to handle change, you should also get some indirect supervision of the kind of change one can expect. So therefore, along that lines, what we propose is that you should actually, take effort to attach extra metadata with your training data. So you can actually think of your training data as comprising of a mixture of groups or domains. So, so this training data we think of, and let's say, you are told that the training data obtains from, say, 5 different domains. Going back to the speaker example, it might be like 5 different accents. So you are given this grouping information in the training data. And you need to not just generalize to more examples drawn from within the domains which are given to you, but also for new domains which you have not seen during training. So that is the challenge we want to sort of address in this talk. How can you generalize to new domains which have not been seen in training by exploiting the inter-domain variation among the domains that you see during training? So before we kind of go into, the techniques which have been proposed, I just want to give you a very simple toy example just to sort of, help us define the problem better and make it very concrete, what we hope to do with exploiting group information. So let's consider this very simple data set which resides in 2 dimensions. So you have 2 features. So this is X1 feature and X2 features. And we have 2 labels which are indicated by the colors of the points. Now, suppose, each of these cloud consists of a large number of points. So there is no issue of, sort of model selection, making of too many parameters. Let's say that's not a concern. So in the sort of limit an optimal, just based on what distribution you see pictorially here, a good classifier, which you might derive based on, say, maximum likelihood estimation principle. If you just assume that all these examples are IIT samples, would be, say, maybe drawn by this green line. But on the other hand, if I give you group supervision, then I would actually, let's say, also tell you that, hey, my training data consists of these 3 groups, which indirectly is also a warning that during test time, you might have to handle new groups. So this could be like, say, a test group. Now, on this test group, if you look at the default classifier, the green classifier, it gives you very poor accuracy because it's classifying everything as blue. If all the red points are also below this green line. Whereas our hope is that we want to come up with a good domain generalization but decision boundary, which is denoted by this dashed line. So our goal is to come up with decision boundaries which are robust to domain change. So now the main challenge is, how do we do this for real life data sets and with high capacity neural networks? So we will go over the latest research in the machine learning community to address this challenge of coming up with domain generalizable classifiers by making use of grouping information during training so that you can handle new groups during testing. So this is the outline of my talk now. So we will consider 2 types of domain changes. So first, we are going to consider a somewhat more friendly setting where domains are defined by a single continuous attribute. Let's say time. That's often a continuous attribute which defines domain. And you sort of say, let's say during training data, domain change is defined based on, say, something which is moving along this x-axis, and you are shown 5 groups during training, and you are also told during deployment time, I am only interested in, say, a time interval which spans this region, which is defined by D6. So you are given a domain ID during test time, and your goal is to train a classifier which will do well on D6. You really do not care about the performance of the classifier on the training data. You know that you only want to handle or train the data for the data that you will be seeing in the future. So this is the first part we will be focusing on. Now, the second part, we will go to the more general setup where the domain IDs are not in some continuous space, which is explicitly provided to you. So we just then model the domain ID as some discrete quantity. And you need to handle new domain IDs during test time. So for the first part. So this part arises in many practical situations. For example, if you consider, now recommendation models, those are very commonplace in e-retails and search engines and all that. So all of these companies, they implicitly collect label data based on users clicking on items or articles. So, so they have to, they use the data which is collected, say, up to some previous T days. So you have data collected based on user interaction, say for the past T days, and you train a model. Now, you know that you will only need to handle now the data which you will be seeing tomorrow, which is say day T+1. And also you will be periodically retraining the classifier. So the classifier that you train at this point only needs to do well on this one closed interval of time, because you are going to retrain the classifier after that. So this is the setup. And again, we are going to assume that the change of the distribution along time is gradual. But the challenge we assume is that T is not very large, that you are not given, like if T is like say going into thousands, then many of the things that I'm going to talk about now will be irrelevant and it may not even be required. So we are operating in the setting where T is say, in the order of, say, some like remember 10 or something. Okay. So, and also, many people might think of this as a domain adaptation problem. It is not, because we do not even have unlabeled data in the future, right? I mean, because unless you do time travel, you will not even have unlabeled data for tomorrow where the model needs to serve. Okay. So now, in order to understand the challenges in this problem, and to also qualitatively discuss the pros and cons of various proposed methods, we will again consider a synthetic setting. And later, of course, the method that we discuss, we will apply it on a real life data set with more complicated distributions. By the way, I must say that this is also alternately known as handling concept drift, create training classifiers so that you can handle concept drift. So we are basically trying to discuss on methods of handling concept drift in modern deep learning scenarios. So we are going to work just for the next 3-4 slides with just for illustration purposes with this synthetic scenario, where this is a well-known data set. It's called the 2 moons data set, where as usual we use color to denote the class label, and each dot here is a training examples, and here also we assume that the data has 2 features, x1 and x2. And so then the training data is basically the point cloud that you see over here. And visually now it's very clear what the decision boundary should be for this training data. It should kind of basically go from here and up to there. But we assume that the data is not fixed, but it is changing along time. And the change along time is happening by rotating the 2 moons by 18 degrees in the counterclockwise direction. So when you go from step 1 to step 2, then the x1 and x2 features are rotated by 18 degrees. However, please note that the same training example is not available at different timestamps. If that was the case, then it would become like a sort of a time series forecasting problem. We assume that the distribution has the entire distribution has rotated by 18 degrees, and at each point in time, you draw fresh samples from the distribution. So there is no one-to-one correspondence among the points across the 2 timestamps. So now, suppose if you just use the entire training data and use the default ERM training, then, so here we are assuming that we have rotated the images 10 times in steps of 18 degrees. And so this is the 10th point. So here you see that the starting figure has rotated by full 180 degrees. The red points are above now and the blue points are below. And our goal is to do well in this, that after the rotation has happened by 180 degrees. So if you just train a model on the average of the previous 9 training snapshots, what you will get is basically an average decision boundary, which, the average of rotations from this to the last figure here will be something which is like 90 degree rotated, and the decision boundary that you see by this line and this contour, this denotes the decision boundary by a model which just uses the union of the entire training data. And it's not, of course, an idea that anyone would apply in practice, but I'm just sort of going through, again, this is just going to help us understand the situation better. So this is the default ERM classifier, and if you just use that, you get 78% accuracy. Whereas, this data set is quite simple, and with modern nonlinear classifiers, you can easily get close to 100%. So if you just used in-domain training data, you would get 99.9% accuracy on this data set. So this is not going to work. Now, many of you must have thought that, okay, why would I even use the entire training data? Why would I not use the most recent data? And a continuous formulation of giving more importance to the more recent data is via online learning, which is again another field, which is well known sort of subfield of machine learning. So when you apply online learning on this problem, then you get much higher accuracy. You go from 78% to 85% by giving more importance to recent data. But a problem with just applying online learning is that you might sort of end up ignoring the old data, and also, the future data may not be anything like the past, because it's like, ideally we would like to handle the drift and sort of imagine what the data would look like in the future. So that led us to a whole bunch of people trying to work on data augmentation based approaches. So where you try to kind of generate data into the future by handling the continuous dynamics of the generative process of the data. And if your data distribution is simple, then this is a great idea. And, theoretically, it can work very well, particularly if T is not so small. And so motivated with these thoughts, people have proposed algorithms like C dot. So this is basically like, applying optimal transportation to transform distributions using temporal regularization. So you transport the distribution continuously from, say, T1 to T2 up to whatever many snapshots of data you have in the training time. And you sort of learn these maps while regularizing them so that between two consecutive time snapshots, you don't make very big jumps. So this paper sort of provides one algorithm for doing this task. And but when we try to apply it even on this 2 moons data set, and even by using the latest and greatest of GAN types classifiers, we found that it was very difficult to transport the data. When we try to simulate, generate, transport data between two adjacent time points, this is the reconstruction we got. So red is the ideal distribution and orange is the reconstruction. And likewise, blue is the ideal and this light blue is the reconstruction. And we do this optimal transport all the way from 1 to T. And finally, at time T plus 1, we got this cloud. And now this cloud looks like it could be kind of, it's close to the last distribution. And with that, when we train the classifier, this is using this optimal transport method. So essentially, theoretically, you are doing something correct here because you are imagining what the data will look like in the future, and then you are creating your decision boundary on the future data. And that gives us like almost 91% accuracy. But then this method is not very practical for high dimensional data sets. Like it's not very easy to apply it for anything but these kind of synthetic distributions. So then, we thought, okay, let's try to just learn directly a conditional distribution, which is a function of time. So for that, we try to train a neural network, which will capture the evolution of the decision boundary with time. So now you provide time as an input along with the X, and the classifier that you learn now takes as input X comma time. And of course, theta are the parameters. But when we tried this approach, we found that just simply concatenating the time did not work. And we had to apply some more deep learning sauce and magic to kind of actually get the time sensitive network to work. And here are some details. So the first thing that we did is that we converted the scalar value of time into a vector. So so other people have published, methods of creating sort of these vectors out of time, which takes into account both frequency-based, repetition and also trends. So, you kind of take a point in time and you extract its frequencies and its trends components, and that gives you an embedding of the time vector, and you give that time vector as input. That's the number one change. And second, instead of making all the parameters of the neural network evolve with time, what we try to do is be a bit conservative, and only some of the parameters, for example, the activation thresholds, which are used in ReLU, we try to make it a function of time. And the way we make the threshold a function of time is driven by some additional parameters fees, which are also learned end to end with the overall network. So this gives us a time sensitive network. And the time sensitive network actually was quite good. We got just with this, just by training that time sensitive network and not doing any data augmentation, we got 96% accuracy, which is the best that one can hope for. But we found that when the number of timestamps which are available to you is small, then the time sensitive network is very difficult to train to have smooth behavior a long time, and it does not guarantee that you will generalize to future time. It just makes sure that maybe within the time spans which are present in the training data, you can even apply some regularizations to make the network smooth, to vary smoothly with time, but it does not guarantee that the network will sort of extrapolate to the future. So then we tried to kind of enforce smoothness a long time for the time sensitive parameters. Again, this is a topic on which there has been some prior work. So there has been methods like AdaGraph, which try to impose kernel smoothness of time specific parameters. Other people have proposed Gaussian processes of the last layer of the neural network, using which gives you the smooth decision boundaries, as a function of time. But actually these methods, again, when we tried it for the range of data sets that we are even interested, we found that they did not scale well. So finally we came up, so this is the last slides of approaches that I'm going to talk about. So this method that we came up with is this gradient interpolation loss. So the basic idea is very simple, that you have a normal loss which tries to reconstruct the y based on the f theta. But in addition, what we try to do is to predict the loss on the logits which are computed on first order Taylor expansion of f x comma theta. So what this does is that, if you have an x which was provided to you at timestamp t, you sort of calculate the logits of nearby times, including, like, say, t minus delta or t plus delta also. So we consider negative values of delta. So you take an x and you kind of just shift it by delta, and you calculate the logit at t plus delta, and then you adjust it based on the gradients so that you get the logit at time t, and you use that to impose the loss. So what this provides is some kind of a supervision on nearby time steps, and it encourages smoother functions. And when, as I mentioned earlier, when delta is negative, you can even extrapolate. So if you have been given data up to some time t, then you can also sort of pretend as if the time the data exists at t plus delta and apply the first order Taylor expansion to kind of indirectly supervise it. So with this method, actually we got finally the best possible accuracy that one can get, at least empirically, without assuming labeled or unlabeled data in the training domain. And so this is what we called as the GI loss. So this work has appeared in NeurIPS 2021 this time. And so this training algorithm requires a bit of care. So here, first what we do is we pre-train the time-sensitive networks on the training domains with standard expected risk minimization. And then we fine-tune using the gradient interpolation loss, where for each mini batch, we sample a delta first uniformly within some range. So this is a hyperparameter of our algorithm. And then we try to find an adversarial delta. So the delta on which currently we get the maximum loss. So for that, we have to solve another inner loop optimization to find currently the delta which is most violating the smoothness constraint that we would like to enforce on the fx comma t xx comma t function. And then we clamp delta to be within the range. And we use this adversarial value of delta to finally solve for the theta using the GI loss. And now we try to apply this on several classification and regression tasks. And we compared with, as I said, concept drift is not a new problem. There many different methods have been proposed, including, some optimal transport-based methods, some adversarial training methods, the smoothing method like AdaGraph that I discussed earlier, and online learning. So we tried with many different such methods across both classification and regression. And we found that with GI loss, we mostly do much better than existing methods. And so this is like 1, 2, 3, 4, 5, 6, 7, 8 data sets. So it kind of inspires confidence that it kind of works well or across 8 different data sets. And then we also compare the GI method with other methods of regularizing the time sensitive network. So, actually there are a bunch of methods which exist again in deep learning called, say, training with adversarial loss. So we applied that as time perturbation. We also tried to regularize the gradient independent of the GI loss, and none of them worked as well as what we are obtaining through this method. So basically, in summary, what I want to say here is that we used 2 techniques to prepare the network for handling future change. One is we made the network parameters time sensitive. And in order to make the network parameters time sensitive, you have to engineer it well with proper time to vectors, etc. And you have to kind of make some careful choices about which parameters you will make time sensitive and not. So one setting which worked for us I had presented, but for some other problem, some other setting might work, who knows. This is deep learning. And then we tried to supervise or regularize the time sensitive network via the gradient interpolation loss, and the particular form of the loss is very important, and you cannot get the same effect by simple gradient regularization or other smoothing techniques that are out there. So this brings me to the end of the first part of my talk. Let me see how we are doing on time. Okay, so as per me, we still have 23 minutes left. But on the other hand, if there are some quick questions on the first part, I can take that before, or should I just continue with the second part?
I don't see anything in the Q&A box.
Okay. Okay. So now we are going to talk about the more general setup of domain generalization. So here we are going to, so here in this setup, we are going to assume that during training, we are given the input X and label Y and a discrete domain ID D. So this D belongs to a discrete set D1 to Dk. So just we are saying that the label data is basically a union of these K distributions. But during deployment, we will not be given the domain ID of the example on which we have to make prediction. And we have to do well on the K domains which we see during training, and also on new domains which we may not have seen. So that is the challenge. So now why is this a hard problem? So the main reason why this is challenging is that, the input X can be a deeply entangled function of the label Y and the domain D. And during training, we are only shown a limited number of distinct domains. And during test time, the domain is not observed. And modern high capacity neural networks can very easily overfit on the few domains that are shown during training. So whereas, we would like an ideal domain generalizing classifier to not depend on that part of X which is determined by D, but extracting the part of X which is independent of D is non-trivial. So that's our challenge. So again, we will illustrate the challenge with a toy setting, just to again, kind of get the intuition in your mind. So let's consider this simple setting where we have training data like this. Here again, color denotes the label, and the shapes denote the domains. So you have the circles, which is domain 2, and you have the crosses, which is domain 1. Now, unlike the previous examples that I had shown, here we assume that the noise or the spread of points also varies from domain to domain. So you assume, so this is sort of the generative model we use for drawing this diagram. So we assume that X is equal to Y times some common feature, which is EC, plus some domain specific weight of a domain specific component, ES, and there is some noise which is also domain dependent. So the covariance function is domain dependent. So here you see domain 2 points have a larger spread than domain 1 point. So now we want to, and of course we want to generalize to new distributions, to new domain distributions. So suppose if I sample new values of D, then I might get a new distribution, say denoted by this triangle. So I want to train a classifier which will also handle these new domains. Now, if I just use the ERM classifier, then the default ERM classifier on, ignore these points which are within the dashed circles. Those are not seen during training. If I just use the training points, then I might get a classifier like this. And now this classifier performs poorly on the new domains which are seen during test time only. And our goal is to, of course, generalize to this new domain. So this is our challenge. So again, please keep this diagram in mind when we discuss various approaches. So even domain generalization, although it's not as old a problem as concept drift, over the last 4 years, there have been many papers on domain generalization. It's overwhelming and depressing to see that many papers. But so I'm just going to kind of discuss a few of those most popular methods. So one sort of general thought behind domain generalizing classifiers is this very intuitive thought that when you train a neural network, you want that the last feature which is used for the classifier should not have any domain signal in it. So these are called domain erasure methods. So the starting point is that when you do normal training with seen training domains, then you could overfit on the training domain. I'm kind of showing it with colors here. So suppose if you have trained a network with red, green, and blue domains. Sorry, these should not be thought of as labels. These are domain colors now. So these 3 domain colors, if you have, then various parameters of the neural network, like the softmax layer and the last features, they will have domain, they might overfit on the training domains. Whereas what these domain erasure methods want to do is make sure that this last layer and the softmax parameters do not contain any domain signal. And they achieve that by adding these domain adversarial networks, which try to make sure that this last layer features H cannot find any domain signal. So this way you're wiping out the domain signal. So many papers have proposed these class of methods, which are the domain erasure methods. Now, a problem with this approach is that it's very easy for a neural network to overfit on the training domains on everything below the last layer. For example, in the worst case, the last layer could just output the label distribution, and then you will not see any domain signal, but that does not mean that the whole network will generalize to new training domains. And another problem is that the accuracy of in-domain data might suffer. And of course, the other problem for if anyone who has tried to train these networks which have these adversarial networks like GANs and all, you find that training such models is highly non-trivial and it can give rise to very unstable training. So, if you try to apply these domain invariant methods, then, for the distribution that, given the generative process that I've shown on this side, the ideal classifier, it's not very hard to see, is the one which does not depend on the y-axis at all, which only classifies based on the x-axis, because that is the common feature. Whereas the y-axis here determines the domain-specific features. So now this is our ideal classifier, but if you try to use the domain erosion methods to recover this domain generalizing classifier, you will find it to be very tricky, because the way we have, in this data distribution, both this axis contain domain specific information. Because the variance is different for different domains, so because of that, you cannot actually get these domain invariant methods to work well, because both the features reveal domain specific information. So that got us to kind of try to think of something, which does not even try to apply domain invariance, but just ensure that you will generalize to new domains through data augmentation methods. So this is like a totally different way of trying to do domain generalization. So in the domain adversarial method, you try to latch on to features which do not change a long time. Whereas in data augmentation methods, you try to simulate or hallucinate new examples which come from nearby domains. And because you are training with a larger number of domains, where some of the domains are synthetically generated based on, again, the magic of deep learning, you can hope to be more robust to future domains during test time. So this method is particularly useful when it's very difficult to separate the label and the domain features. So with that, we are hoping that even though your training data, let's say, has examples from 3 domains, you hallucinate examples from 2 more domains which are nearby the current training domains, and now your network can handle more domains, as demonstrated by this very colorful last 2 layers. Now, implementing that in practice can be challenging. So we had this paper in ICLR 2018, where we proposed a simple sort of gradient-based method for generating examples which differ, which, we basically take the existing training examples and perturb them slightly so that they change along directions of domain change. So in order to do that, here we have, like, say, normally you take an X and you have a neural network which will predict the Y. Now what we also propose is that you take the X and you have another neural network which will try to obtain the domain. And now for an example X, we perturb this example along directions of domain change by calculating the gradient of the domain loss with respect to X. So we add the gradient with respect to domain change to X, and we sort of assume that this is our hallucinated example, which differs slightly from the domain of X, and we train the classifier with this hallucinated example. And in order to make sure that this path of the network does not contain any label signal, even the domain classifier we train with examples which are perturbed along directions of label change as against domain change. Okay, so with that, we call this cross gradient training. So with that kind of a training, we got a modest amount of robustness to domain change. So in terms of the loss function, what we do is this, that, so if you have like theta y denotes the parameters of the label classifier and theta d denote the parameters of the domain classifier, then we train the classifier, our network, in addition to the usual ERM loss, which I have not added. We have these two more losses, one which will try to optimize theta to work well on X, which have been perturbed along directions of domain change. And we also try to train the domain classifier on examples which have been perturbed along directions of label change. So with that, when we try this data augmentation approach, so suppose if you have examples like these, then with the data augmentation approaches, what we will hope, I have not shown it pictorially, is that you will get some more points sort of in the shadow of the current training domains. Sorry, I don't have the figure here. And with that idea, we found that compared to existing domain adversarial network methods, and of course the baseline ERM method, and other methods which are used to increase robustness of neural networks, we found some modest gains on these 4 data sets: handwriting recognition, font recognition, MNIST digit classification, and ASR task. But there were, this method also had a bunch of limitations. First, we found that, the domain classifier may not find all domain revealing feature, because the domain classifier just wants to extract the domain ID. And as long as a subset, as long as it finds some feature that can reveal to it the domain ID, it will be happy. And then the perturbation may not be exhaustive. Whereas if you want to train a network which is robust to domain change, it should be perturbed along all domain revealing features. Okay. And the second problem, of course, is when you do gradient-based perturbations, you cannot take big jumps, because then you might generate a very, garbage instance, like an image, which is not even recognizable. So we had to make only very conservative perturbations. So because of that, we got only modest gains. So that kind of brought us back to thinking again about domain invariant methods. So suppose if we really, we want to go back to methods which try to depend only on features which will generalize or which are common across domains. So, we found that that domain adversarial classifiers were difficult to train. So, is there an easier algorithm for extracting the shared features across domains? So with that as the objective, we proposed this method, which is this common specific decomposition method. So here the idea is very simple. You take your network H, and the last decision boundary, say the softmax parameters, you kind of factorize it. So the last softmax parameters for, say, domain D is factorized as a sum of some parameters which are, we call the common parameter, which are shared across domains, and some domain specific parameters. So these are the domain specific features or parameters, and there is a domain specific weight. So with this factorization, we sort of train the network. And in order to make sure that this parameterization is identifiable, we have an additional orthogonality constraint on the common and the specific features. And during training, we impose loss on both WC and WD. And during deployment, once we have recovered the common features, we do the classification only on WC, and we just throw away the WS. So now this might look like, why should this method work? What is the, what's happening here? Suddenly I started talking about this decomposition and what is the basis of this idea. So I would like to go to that as soon as my slides refresh. I'm getting some network problems, sorry. Yeah. So just, oops. Hello. I think, my network, sorry, my PowerPoint crashed. I have to reopen it. I'm going to restart my PowerPoint. I'm sorry about that. Oh, okay. Okay, looks like we are back online. Sorry about the interrupt. So, so this is just showing the same, CST in color format. So essentially, we are saying that there is this common parameters which are shared across domain, and we have domain-specific weights multiplied with domain-specific softmax parameters. So why should this idea work? So, yeah. So why is this a good idea? So, there are particular kind of generative models where we show that this particular method of training classifiers is optimal when you consider linear classifiers. Specifically, if you assume that your data X is obtained through this kind of a generative process where you have a label Y and there is a common feature plus some domain specific weight and some domain specific features. And you can have a whole bunch of domain specific features. Here for simplicity, I'm just showing one. And if you have domain specific noise, so if this is the generative process, then it can be shown that the optimal domain generalizing classifier is a sort of WC star, which is obtained by the common feature EC minus the projection of EC on the domain specific features projected out. So once you do that, now, so this is the optimal domain generalizing classifier. So the question is, how do you extract this optimal classifier without knowing EC or ES? Okay, you are just given samples X and Y, and how do you extract this WC star? So the recipe that we propose is that you obtain per domain classifier WD, and then you want to factorize the per domain classifier into this common part and the domain specific part. But there are many possible ways to achieve such factorization. However, if you additionally in this factorization constrain that WC is orthogonal to WS, then we show in the paper that the WC that you obtain through this factorization will be the optimal domain generalizing classifier. So the WC star, the WC that we will obtain through this factorization will be depending only on those features which do not carry any domain specific variation. So you could see the proof in this paper. And empirically also we do well. So this is a speech task. I will not go into the details of the experiments. And this is another handwriting recognition task where we have compared with many different state-of-the-art domain generalization methods, and we do well. So in summary, for domain generalization, what I would like to say is that the CST algorithm is a simple and efficient solution to domain generalization, and it is very practical. Its runtime is only 1.1 times the ERM baseline, whereas all other approaches like the adversarial approaches are significantly slower, including our own cross-grad algorithm. And it's also, of course, easy to implement. Also, you just modify the last layer. But a downside of this algorithm is that it's not very good for in-domain data. So it does well only on, sort of domains which are outside the training domain. But in practice, you will be seeing examples which are both from within the training domain and outside the training domain. And for that, we need new methods. So this is, I would say, an area which is still open for more exploration. So in summary, what I try to impress in this talk is that maximum likelihood estimation based training, it ensures generalization only when the data distribution does not change after training. But if you want to prepare for change, and change which we think of as natural change, then a good strategy is to actually just view your training data differently. Try to associate additional metadata in the training data so that you can sort of identify groups which characterize units of change in the training data itself, and design special purpose algorithms which ensure generalization to these groups across changes of the groups. So for gradual drift along time, we proposed the simple gradient interpolation loss, which was much more effective than prior, more elaborate methods. And for unknown discrete shifts, we proposed a simple factorization of the softmax parameters to achieve domain invariant decision boundaries. So what next? So currently we are trying to theoretically analyze the two new loss functions that we have proposed. In practice, we see that they work well, but we would like to kind of also understand, provide learning bounds, in theory. We would like to also do more extensive evaluation on real world scenarios. Another sort of problem related to robustness is handling subpopulation shifts. So like if you train on a bunch of groups, you want your model to not have very poor accuracy on any one particular group, specifically say a minority group, which has negative interference with other, say, majority groups. This is also related to the point of spurious correlation, on which now there is a lot of interest in machine learning. So for example, if there is a majority domain which has some easy features, but which conflict with a minority domain, then, the minority domains can get very poor accuracy, or the network might overfit on the minority domain. So how do you handle such tricky scenarios? Another is handling heterogeneity of domains during training. The different domains might differ a lot in the amount of label data they have. The class ratios across the different domains can differ significantly, or the amount of noise or difficulty of training classifiers can be different. Finally, currently we are working on the fly unsupervised adaptation of machine learning models, while also generalizing to new domains. So if you have, in the training data, in the test data, if you don't have just a single example, which is kind of very difficult to handle well, but suppose if I give you a small group of homogeneous examples, then can you do on the fly unsupervised adaptation when that new group is different from the training groups, but when it is from the training groups, then can you choose the best possible expert for those group of examples? So with that, I would like to thank you all for listening, and I can take questions now if there is time.
I don't see anything in the Q&A box.
Okay.
Are there any questions? Sanjay Bhatt is raised there. Sanjay, go ahead.
Yeah. Hello, Professor Saravagi.
Yes.
Thanks for the very good talk. Just kind of a speculative question. So some of the ideas that you have outlined here, maybe you could indicate to what extent or in what way they could carry over to time series forecasting.
Actually, for time series forecasting, you can do much better because you have the same, point at many different timestamps. So you can actually model how a particular point is changing along time. So you can do much better than, say, using the gradient interpolation loss.
Okay, thanks.
Yeah, I have a question.
Yes.
The part where you use this time dependence.
Yes.
So instead of assuming explicit time dependence, why not assume dynamics for the underlying model itself and use a recurrent neural network?
So you would give, but if you're using a recurrent neural network, you would have to have the same inputs value at different points in time. And we don't have that. So, we have
No, it's not only a parameter shift. If it was just a parameter shift or something, you could probably model it as some kind of dynamics. It's completely different entities entering the picture. Is that what
yes.
you mean?
Yes. Yeah.
Any other questions? So, if there are no more questions, I'll ask Sanjay Bhatt to make some announcements before we thank. Maybe we'll thank Sujita first. Let me thank on behalf of everybody for a wonderful talk. And Sanjay, go ahead.
Okay. Thanks.
Thanks.
Yeah.
So I have three quick announcements. The first is all the registered participants must have received an email last night sharing the link for downloading the proceedings for the conference. So I hope everyone received that. The second is a pleasant task, since we are not going to be meeting together again for the rest of the conference. We will all split up in different sessions. So it's my pleasant duty to thank on behalf of all the organizers and all the various chairs who have put this conference together. Thank various people who made this possible. So I'll very quickly do that. The first is the International Program Committee, who helped put this program together, as well as the anonymous reviewers. Then the second is the plenary speakers who graciously accepted our invitation to give us these really nice talks. Then I want to thank the IEEE Control System Society, whose grant from their outreach funds helped us support close to 80 to 90 students to attend this conference without any registration fees. This year was a kind of outlier because we didn't have to support travel and accommodation. So we were actually able to also use the same funds to fund a small number of faculty from colleges other than the IITs. Then I also thank the sponsors, our sponsors, TCS Research, Tata, the Technology Innovation Hub for IoT and IoE from IIT Bombay, and MathWorks for generously supporting this conference. I also want to thank our IT partners, Epsilon India Private Limited, as well as Mr. Sarkar from KW Conferences for all the support they provided. This platform on which we are having these virtual meetings called Zoom events is a relatively new offering, and actually identified it for us and helped set it up, and I hope everyone agrees that it has been a smooth sailing for us. So in our line of work, Epsilon usually stands for a small quantity, usually to be neglected, but in this particular case, Epsilon really made a big difference. Then last but not the least, I want to thank the group, very good band of volunteers that Professor Dev Satampal put together. We lovingly call them the Dev Sena for their stellar support in carrying out all the sessions very smoothly. So thanks to all of them. The last item on my list is concerned with the Best Student Paper Award. So this is a feature that has been a fixture of ICC at the Indian Control Conference right from the very first edition. And the purpose of this is to encourage our students to write better papers and also present them better. And the way we try to do this is to try and get feedback from experienced researchers and get it to the students who submit their papers for this award. So this year we received 13 nominations and a set of 4 reviewers. These are different from the reviewers who reviewed the paper in order to decide whether they can be accepted to the conference. So this is a different set of reviewers who screened all the submitted papers and shortlisted 3 finalists. And then these same set of reviewers all together collectively read these shortlisted finalists again. So the list of finalists is on our website. And then the same set of reviewers also looked at the video presentations that were uploaded by the finalists. So there were 3 finalists. I think 2 of those finished their presentations this morning, and I think one of them is this afternoon. So you can find the sessions and attend their talks. So based on the scores that these reviewers assigned to the paper as well as to the presentation, so these are all separately evaluated. We finally have the winner. The winner is, I'm just going to share my screen. Oh, just a moment. Let me see if I can share my screen. Yeah. So I hope everyone can see that. The winner is Shivam Dhama for his paper titled Asymptotic Analysis of Discrete Time Models for Linear Control Systems with Fast Random Sampling, co-authored with Chetan Pehlajane. So we'll be sending this certificate to Shivam Dhama over email. Just a minute, I need to unshare. Oops. Yeah, I hope I am able to stop sharing. Anyway, so that was our winner for us. So please join me in congratulating the winner. And that's the end of my announcements. And I hope to see you in the 2 sessions that are remaining. Thank you very much for paying attention.
Thanks everybody for attending, and I don't know if Sunita is still around. Yeah, Sunita, thanks again for the talk. And I also thank the support given by the student volunteers, which made everything go through smoothly.
You're welcome. Thanks. Yeah. Bye.
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 Thank you, everyone. I'm going to end the meeting now.